So I'll briefly share a set of slides, just mostly to show some interesting images and ideas. So this is like a project like that I like to call an Academy of Spatial Agents. That this is like one of my first prototype for my PhD research. So the idea is that if you think about generative systems for design, the idea is that you have a group of designers that they formulate a generative system. So they bring some design knowledge, expertise, a rationale, and they create like a model that's able to generate design alternatives. So they formulate, someone codes that model, and after that they can interact with that model. So for example, this example has like chairs in the design space. So after the model is developed, they can interact with that model. However, if you think about spatial synthesis, the field that's concerned with developing like spatial configurations, and most of the, let's say the mainstream techniques, they are like destructive techniques, sometimes optimization based. So in general, you end up with this workflow where the designer provides a certain input and the algorithm computes like maybe trying to find the best alternative, or gives you like 1,000 alternatives. Or the designers can also develop like a set of rules to generate spaces, but that's also challenging. So I've been looking for an alternative way of developing like generative systems for spatial design. And the basic motivation here is that you understand design as a type of dialogues, not so much I'll give a problem to my model and it will develop the best solutions. The idea here is that the designers want to collaborate step by step with the generation of the alternatives. So it's more like a dialogue with fine-grained interaction, and explore the design space together with the model. And you can bias the search, and you can look for local and partial solutions. So I think there are a lot of benefits of this approach. And that's where reinforcement learning comes to play, because you have like agent-based models, but in general, they come from other areas. Like if you think about like, I don't know, swarms, voids, like you have a lot of models, they come from different fields. So it's a little bit challenging to adapt them to say, okay, now I'll take this model and I'll develop a layout, a floor plan. So reinforcement learning in my research, I use it as a way to, let's say, as a way for designers to create their own like agent-based models. So the designer can create like a reward function, can encode some goals, and using reinforcement learning, they will develop agents that will achieve those goals. So the designer provides like what the agents should be able to achieve, and the agents learn how to do it. That's more or less the explanation. And you can see in the image here, the idea that you have something that's dynamic, that's very interactive, and you can interact and you can change parameters, or you can directly interact with that. Yeah, maybe I could share some lessons for researchers, but I think one first lesson, just like parenthesis here, it's like when you're developing research with reinforcement learning, always start with a simple prototype. It will become more complicated than you expect. Reinforcement learning is not simple. At least today is not simple. So the challenge is like, okay, I'm going to use deep reinforcement learning. So I'm going to use neural networks, and I want to train these agents. So how I'm going to represent these agents, how I'm going to represent their actions, how I'm going to represent goals. I think people who are more interested in these details, there are some papers that are published, but I'll briefly show here some images showing like in this prototype, I used like a very, let's say, classical representation that's a grid, because then I can use convolutional neural networks. So I can have like multiple, for the state of the agent, I can have like multiple layers indicating different aspects of the agent, like the goals, the types of cells, the shapes, things that will inform the algorithm, will inform the model. So basically the representation is based on layers with information, and the agents are like polyominoes. So the sets of cells that share edges, and they have a perception around it, and they take actions basically by expanding or retracting, like select one cell, expand, erase, or add one cell. And that looks very simple, like, okay, so I have this set of cells, and it can add one cell, can remove one cell. That looks like too simple. But I think that's the interesting part, like the reinforcement learning model will use those building blocks as a way to create more complex actions. So you have like spaces, each agent here is a space. The space can like reshape, the space can move quickly to another position. So there are a lot of like complex behaviors that emerge out of that. I think that's lesson number 2 here, is that for me, when I look at these grids, I'm very excited. Wow, look at these, very interesting how I'm representing like adjacency between spaces and areas. And when the agent starts to learn, that's very exciting. But I need to be aware that my audience is not necessarily made of computational designers interested in reinforcement learning. So in actual reinforcement learning works with like representations that in general they have like a lower resolution. Like this case looks like probably like, I don't remember, like 16 by 16, 12 by 12, very low resolution. So when you show to designers, they're like, all right, that looks like a grid of cells. Like, I don't care. So it's hard for designers to understand and to see how the knowledge in terms of behavior is being embedded there. So the challenge is that you also need to develop representations that are specific for your audience. And that's where, when after training, I trained these, you can see the details in the papers, but I trained these agents to try to solve like adjacencies, certain areas and shapes, and the designer can change the parameters of these goals. So I trained these agents, and I'm trying to figure out how to generalize that knowledge, like to, let's say, to novel situations, to design problems. So this is just like an example where I take these agents and I use each of the agents to represent a space in a house. And I establish adjacencies, I establish like the areas. And I release these agents in an environment with obstacles, and I let them develop the kind of like this layout floor plan. And I keep adding, in this case, there's no user interaction. I'm adding noise. So I keep adding noise to see what happens when the agents like, the agent can select actions to try to develop the layout, but at the same time, it randomly selects some actions, some disturbing. So the agent has to figure out another layout. And as you can see, I think I like the part where there's a lot of noise. I think you're going to see it soon. So you have kind of like a layout working on here. Yeah, and then you have noise, there, a lot of noise. And then the agents have to recover and find another layout, which is really interesting. But at the same time, you can see that I have a parametric model over the agents. So I have windows, I have walls, I have doors, I have like some areas that are 2 agents that are considered part of the same space. There are no like divisions. So I have a layer of like geometric entities and control over that. And that's where that last lesson is important. Like when I show these to a designer, the designer can understand, whoa, now we have agents, they're like generating spaces, look at that area. And I think that's important for researchers. And here at the bottom, you can see like 3 different environments with different obstacles. Some results, you end up generating like completely different layouts, even the layouts with a lot of noise, a lot of randomness. It's kind of like interesting. But this type of model, like this is an image of me talking to Jimo, and we're like, I'm showing to Jimo, this is what I'm doing in my research, take a look at these models. And immediately his reactions, like, we are on a Zoom conference, like to start sketching. Oh, look at this is interesting. You have like an empty space here. That's very interesting in terms of design. Oh, look at this glass wall. He starts sketching on that. And I think that's important because that's where design happens, when you start like interacting with the models, right? So in this research, I've been trying to integrate learning, agent-based modeling with goal parameters, and parametric modeling. And I think there's a potential for developing custom agents for designers. There's a potential for real-time collaboration. And currently, I'm trying to bring that interaction that I have just mentioned. I'm trying to enable designers to actually interact with the agents using game engines. And I'm also improving the reinforcement learning workflows, and I'm testing different policies and so on. So lesson number 3, this is more for computational design researchers. Like, custom code is good, but then whenever you can, use libraries. The reason is like when your project starts to escalate in terms of complexity, like in my next steps, I'll show a video here. I'm integrating like Unity game engine with parametric modeling, with like a backend in Python, with PyTorch. So you have all these things together. And sometimes you need to test multiple algorithms. So when you work with libraries, that makes your life so much easier. So even though you want to code everything, you want to understand everything, it's good to work with libraries. That's another lesson. And here's some images of my work in progress. I think this is the first time I'm showing these images, these videos actually. So this is more like what happens when you can actually interact with these agents in a game engine, like in real time. You can change like parametrically, you can change the geometry, but you can also grab the agents, change the shape of the agents, and so on in real time. So you can see that you can kind of like, it's more or less like sketching. You can shape your design, you can interact with your model, and the model gives you something back, like trying to satisfy the goals. And you discover, like, what I think is really interesting is like, instead of thinking about, I'll find the best solution, no, I'm finding multiple solutions where the designer is trying to bias that solution. So I find like partial solutions that are very interesting. They might not have the best scores in terms of like utility functions or whatever, but the designer thinks that's a really good solution. So the designer should be able to find it. So I think for me, this is very exciting. So this is what I wanted to share.
This quite interesting work.